Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss nuclear fission and nuclear fusion. Let's begin. Nuclear fission. This is a nuclear reaction in which a heavy nucleus, those nuclei having mass number greater than 230. In this type of nucleus, the neutron proton ratio is unstable. That heavy nucleus breaks into two or more fragments of nearly equal size with the release of a large amount of energy. A heavy nucleus breaks into more fragments of lighter nuclei with the release of large amount of energy. That type of nuclear reaction we call fission. That fission may be spontaneous or induced. Spontaneous in the sense it radiates naturally. Naturally that heavy nucleus breaks into lighter nuclei. Induced fission means we have to carry out that type of nuclear reaction. Here we discuss about induced nuclear fission. Example: when a neutron particle neutron particle is bombarded with uranium nuclei, that is 92 uranium 235 with high speed. Therefore, that uranium 235 now changes to uranium 236. That one is unstable. That heavy nuclei of that uranium now breaks into the nuclear fragments as barium 56, barium 141, krypton 36, krypton 92, 3 neutrons with a release of huge amount of energy Q, that is the energy released. In that type of induced nuclear fission, when uranium breaks into barium and krypton nuclear fragments, it is always not barium and krypton. That depends on various physical aspects. In some time, it may produce SB 51 133 plus NB 41 99 plus 4 number of neutron with the release of huge amount of energy, or it may be XC 54 140 plus SR 38 94, 2 number of neutrons with the release of energy. During the fission of 92 uranium 235 are not always barium and krypton. Other nuclides have also been obtained, and it is understood when we plotting a graph between mass number and percentage of yielding. If we plot a graph in between mass number A and percentage of yielding, means what nuclear fragments are obtained from that type of induced nuclear fission reaction. Plotting of that graph, we clearly seen at the atomic number 90, the probability of obtaining these nuclei is high. Again, at 140, the probability of obtaining these nuclei having the mass number 140 is high. In this way, it is clarified in that nuclear fission, it's always not barium and krypton, but different nuclei are formed as far as their size, nearly equal size is concerned. Next, how much energy is released during that type of nuclear fission? Energy is released during that nuclear fission. We just choose that nuclear reaction into our consideration. When that neutron is bombarded with high energy neutron with high velocity, bombarded with that uranium 235 nuclei, then it produces barium and krypton. So energy is calculated for that particular fission reaction. Mass of uranium nucleus 235.1175 AMU, mass of neutron 1.00898 AMU, mass of barium 140.9577 AMU, mass of krypton 91.9264 AMU, mass of 3 neutrons, 3 multiplied by mass of 1 neutron, that is 3.02694 AMU. Let me calculate what be the energy released. That energy release is nothing but mass defect into c square according to Einstein's mass energy relationship. Therefore, we write mass defect delta M is given as initial mass minus final mass. Initial mass means mass before fission, that is the mass of neutron and uranium. The mass of neutron and uranium, we just add 235.1175 plus 1.00898 minus final mass, mass of barium, mass of krypton, and also mass of 3 number of neutrons. That mass 140.9577 plus 91.9264 plus 3 number of neutron, that is 3.02694. That addition result as 235.91104 minus this addition result as result as 236.12648. This result 235.9104. Finally, it is 0.2154 AMU, atomic mass unit. Let me calculate the energy released during the process. Therefore, energy released during this fission 0.21544 into 931 mega electrovolt, which results 200.5 mega electrovolt, which is a huge energy. That is energy released during that process, delta m into c square, according to Einstein's mass energy relation. When c square is multiplied to that mu, so it will be found that 931 mega electrovolt unit. The energy released during that fission process is 200.5 mega electrovolt, which is so huge. Another concept in that of fission reaction, which is the idea of chain reaction. Chain reaction is a propagating process in which the number of neutrons goes on multiplying rapidly till whole of the fissionable material is disintegrated. Here the fissionable material is uranium. When that neutron is bombarded with uranium, it produces 3 number of neutrons, 1, 2, 3, and barium with krypton. In that of particular process, 1 neutron is lost and another neutron further bombarded with that of uranium. Again it creates 3 neutrons with barium and krypton, 1 neutron lost, another 2 neutrons bombarded with again uranium nuclei, and it produces 3 neutrons, and that process is continued like this in a chain process until unless that uranium nuclei is not disintegrated, till that reaction is continued. That type of reaction we call chain reaction. And this is a particular type of chain reaction which is called uncontrolled chain reaction. We can't control that chain reaction, it is continued. The best example of uncontrolled chain reaction is an atom bomb. In case of atom bomb, that type of principle holds. Therefore, we achieve a huge amount of energy from that of atom bomb due to this uncontrolled chain reaction. How to control that chain reaction? The chain reaction is controlled if an average 1 neutron per fission causes another fission, then energy will be released at constant rate. Let that neutron is bombarded with uranium, it produces barium krypton with 3 neutrons. 1 neutron is passed through a moderator and another 2 neutrons are absorbed by the observer. So the passed neutron through that of moderator again bombarded with that uranium, and it produces like 3 neutrons, 3 number of neutrons, and again 2 neutrons are absorbed, 1 passed through the moderator, and so on. So as far as our will, we achieve the amount of energy required to us, and it is in a controlled manner. So that type of chain reaction we take place in that of situation called controlled chain reaction. Controlled chain reaction. And the best example of such controlled chain reaction is nuclear reactor. In nuclear reactor, by using that particular phenomenon, we create huge amount of energy as far as our will is concerned, or we can say what amount of energy is required to us that can be achieved by using that type of chain reaction. The best example is nuclear reactor. Let's come to nuclear reactor. What is nuclear reactor and how it is helpful to us to produce energy by using that controlled chain reaction process. So nuclear reactor is a device based on controlled nuclear chain reaction, wherein the nuclear energy produced is utilized for constructive purposes. In case of atom bomb, that is uncontrolled chain reaction and a huge amount of energy is produced. It is explosive and it is used for destructive purposes, whereas in controlled chain reaction, as that nuclear reactor working, and that energy produced here is used in constructive purposes. The parts of nuclear reactor: a core of nuclear reactor, that is the core of nuclear fuel. This is the figure of a nuclear reactor. One of such nuclear reactor part is a core of nuclear fuel. Nuclear fuel where the fissionable material is placed, like uranium 235, called the nuclear reactor fuel. Nuclear reactor fuel, and it is placed in that of core. This is the core of nuclear reactor where the fissionable material, in that of particular case, that is 92 uranium 235, is placed in that of core. This one is fuel element uranium. Next part, reflector. It reflects back some of the neutrons that leak out from the surface of the core. In that of chain reaction, 3 neutrons are produced and 1 is lost, but that lost neutron is passed through that of modulator. In that of particular nuclear reactor section, that reflector is used to reflect back some of the neutrons that leak out from that of surface of the core. Here is the reflector. Next, moderator. It is slow down the fast neutron produced in that of fission process when thermal neutrons strike the nuclear fuel. This is the moderator that slow down the fast neutrons produced in that of nuclear fission process. Control rods. This is the controlling rod. Here is the cadmium controlling rod. Cadmium is used in that of controlling rod. What will be the function of that controlling rod? In order to control the fission process, it is used. Otherwise, the chain reaction may become explosive and damage the nuclear reactor. Therefore, that rod is used for controlling perspective, and it is measured by a term, reproduction factor. This is the technical term, reproduction factor, that is the rate of reduction neutrons divided by rate of loss of neutrons. If that k is equal to 1, then the chain reaction is just proceed. If k is less than 1, then that chain reaction is stops. If k is greater than 1, then that reaction will accelerate. On that basis of this technical term, which is reproduction factor, we say what will be the function of that particular control rod that manages that controlled fission nuclear reaction. Next part, coolant. This is the coolant. The function of coolant: the fission produces heat in the reactor core. Due to that of fission, a heat is produced. The coolant transfers this heat from core to the heat exchanger. That coolant transfers that heat to that of heat exchanger. This is a heat exchanger, which is steam to be turbine, that is water. This one is the steam to be turbine. That coolant transfers this heat from the core to the heat exchanger, where steam is produced. This steam produced at a high pressure runs a turbine, and electricity is obtained at that of generator. In that of steam, which is the pressure vessel, in that of steam, a high pressure runs a turbine. Due to the running of the turbine, and electricity is produced at that of generator. The dead steam from the turbine condenses into water and is returned to the heat exchanger. The steam which are under high pressure are produce electricity. Otherwise, the dead steam from this turbine are now condensed into water and returned to that of heat exchanger, whereas the process repeats and a continuous supply of electricity is obtained. In that of session, we have the electricity. The coolant basically used to cooling that heat produced from that nuclear fission reaction. Next, radiation shielding. This is the radiation shielding. Shielding basically is a concrete constructed around the reflector is known as shielding. Why it is used? Due to the harmful radiations are produced during that process. In order to protect that harmful radiations, we use shield. That shield is a thick walls of cement and concrete which constructed around that of reflector in order to protect us from that of harmful radiations. This is all about the nuclear reactors. Next, nuclear fusion. Another type of nuclear reaction is nuclear fusion. In case of nuclear fission, a heavy nuclei produces or breaks into lighter nuclei, but in that of fusion, lighter nuclei produced a heavy nuclei with the release of huge amount of energy. Nuclear fusion is a process in which two or more lighter nuclei combine to form a heavy nucleus with simultaneous release of a large amount of energy. Here how the energy is released? The mass of the product nucleus is slightly less than the sum masses of lighter nuclei fusing together. Therefore, there is a mass difference which is called mass defect. We denote it as delta m sign that results in release of tremendous amount of energy. According to Einstein's mass energy relation, E is equal to delta m c square, where c the velocity of light. Some example of such nuclear fusion: two lighter nuclei, this is the hydrogen 1s1, 1s1, and it produces a deuterium 1s2 with the release of an electron, neutron, and huge amount of energy 0.42 mega electrovolt. Similarly, another 3 number of such nuclear fusion reactions, 1s2 produces 2he3 neutron 3.27 mega electrovolt. 1s2 1s3 produces 4.03 mega electrovolt. 1s2 produces 2he4 24 mega electrovolt. Look here, 24 mega electrovolt, that is so high energy produced as two lighter nuclei are combined to each other. During that of nuclear fusion, basically the stellar energy, in case of stars, the energy produced due to nuclear fusion, the energy in the stars due to nuclear fusion, and it requires huge amount of heat. That type of reaction we can't perform in just in our laboratory. Why? Because it requires a huge amount of heat, that temperature in order to 10 to the power 7 Kelvin. So the reaction are called thermonuclear reaction. Due to it requires a huge amount of heat, that type of reaction is called nuclear reaction, thermonuclear reaction. Some example has we obtain energy during that of nuclear fusion process. In case of stars, one is proton cycle, 1s1 produce 1s2, one positron plus amount energy q1, and again that 1s1 again fuse with 1s2 and produce 2he3 and energy q3. Then that 2h3 it added with another 2h3 to produce 2h4 and 2h1 with the release of heat energy q3, and that 2 are multiplied to equilibrium that particular nuclear reaction, and finally summing this side we have 4 1s1, summing that side 2he4 2 plus 1 e0 plus q. In that of situation, q is equal to q1 q2 q3, that is 24.7 mega electrovolt. Same thing for carbon nitrogen cycle, when carbon and hydrogen are fused together to produce 7 nitrogen 31 q1. Next 7 nitrogen 31 change to 6 carbon 13 plus e0, that is positron, plus q2. Again that 6 carbon 13 fuse with 1s1 produce 7 nitrogen 14, energy release q3. That 7 nitrogen 14 again fuse with 1s1, produce 8 oxygen 15 and release of energy Q4. Again that 8 oxygen 15 transfer to 7 nitrogen 15 and release Q5. 7 nitrogen 15 plus 1s1 produce 6 carbon 12 and 2 Hc4 plus Q6. Summing up this side and that side, we have 4 1s1 is equal to He4 plus 2 plus 1 E0 plus Q. The total energy released Q is equal to Q1, Q2, Q3, Q4, Q5, Q6, that is again 24.7 mega electrovolt, which is so huge. And that type of reaction we call nuclear fusion, which takes place in stars, and due to this type of nuclear fusion, star produces huge amount of energy, and for that particular process it needs a huge amount of heat, that heat in the order of 10 to the power 7 Kelvin, and that type of nuclear reaction we call thermonuclear reaction. So here with the help of this video lecture we understand the concept of nuclear fission. This is nuclear fission, example of nuclear fission, why the nuclear fragments are not only barium and krypton but another fragments are obtained. This is the nature of these nuclear fragments, energy released during that of nuclear fission process. Chain reaction, controlled chain reaction, this is uncontrolled chain reaction, example atom bomb. Next, controlled chain reaction, an example nuclear reactor. Nuclear reactor, some basic parts of that of nuclear reactor and how it functioning. In electricity production, that nuclear reactor is used. There are so many applications, but most of cases are to produce electricity. Another type of nuclear reaction, that is nuclear fusion. What is nuclear fusion? Some examples of nuclear fusion. During that process the stars produces energy, that is the stellar energy is produced. Two examples how energy is produced during that of nuclear fusion in stars: proton-proton cycle and carbon-nitrogen cycle. So with this useful and informative notes, let me wind up the session. Thank you.